Hello everyone. Today I will introduce my major exam about using OpenMP to QuickSort. My name is Zhang Yunhan, and my professor is Lin Zhenhong. What is QuickSort? You can see the right image. In this array, we have the 5 elements. First, we need to set up a pivot, the best value, and in this best value pivot, we will rearrange the array around the pivot element. And if this right is less than the pivot, it will in the left side, and then it will more than the 6 pivot. It will be the right side, and you can see the 8 is at this correct sort position. So next we need to select the rightmost element as the pivot. And next, we rearrange the array around the pivot element. And then the final step is 10 and the 50 is at this correct sort position. Yeah, so the quicksort is that process. So quicksort have 3 steps. One step is select the pivot. So in my program example, I set up the pivot is the last element, and the second step is the partitioning, and the entire array is rearranged so that all environments smaller than the best value are placed on one side of the best value, and environment greater than the best value are placed on the other side. Once this step is complete, the best value is in this final position. And the step 3 is the quicksort operation are performed on the subsequent to the left and right of the benchmark value, which includes letting the benchmark value or partitioning operation and then recursing. This process is repeated until all subsequents are ordered. Yeah. And next is OpenMP. In my program code, I use the OpenMP to show the memory process and calculate the execution time. And you can see if the origin master string. It has the 3 parallel tags, and in the parallel text one, it has the 3 subnode, but it all in the one line. So you need to calculate A, B, C, and then the parallel text to A, B, C, D. And after we use the OpenMP master thread, the parallel text one will become one line, become 3 subnode A, B, 3, so it can provide more quickly calculate and the process. You will support your execution time very efficient. Yeah. And next is my program code example. In my program code example, I write a main function, and in this main function we have the 4 steps. One step is create an array containing numbers and 1 element, and the second step we print the original data. In this original data, it has the array and the iterate n. And the step 3, we calculate the quicksort execution time. And the step 4, we print sort arrangement and the execution time. And the step 2 is about we need to step 2 function to recall on the compare the element. The one function is the quicksort element. In this function, you need to receive 3 parameters. 1 is the rate, 2 is the low, 3 is the height. And in this function, it will compare the low and the high element and use array low and high parameter to push the partition function to get the P1 element. And we also use the OpenMP to recode the equation start time and the end time. Yeah. The second function is the partition function. We set up the pivot is the array height, and we also set up the I, and its I is the lowest reduced one. And we also use the OpenMP to recode the for loop. Yeah, and in this for loop, we can see you set up the I equal the low, and it will less than the high reduced one, and J will add one. And if the current J precision is less than pivot, I will increase once, and the sweat function will receive two parameter. One is the array I, and the second is the array J. And if the current J is more than pivot, swap function will receive the two parameter. One is the array I add one, and two is array high, and the final will return I add one. Yeah. So we use the OpenMP parallel section directive to the subarray to the side or the right of the pivot. And the subarray on the side, the QuickSort function is called to handle the range of int from low to P1 reduce 1. And second subarray array on the right, the QuickSort function is called to handle the range of the int from the P1 add 1 to high. Step 3, we use the partition function, select the last element as the pivot, and the initial index is I is low reduce 1. I point to the initial position of the smaller element. And for each element is less than or equal to the per volt, increase I by 1 position and swap the element. And finally, place the pivot element in the approach position and return into that position. And swap function is used to swap the value of two elements and print array function. Yeah, and print array is used to print all elements in the array. Yeah. This part is my performance, and you can see iterate one. Execution time is need to use a lot of time, and the second iterator it has the less time, and the third iterator is the very quickly time. Yeah, and last my introduce is my about QuickSort using the OpenMP. Okay, thank you. This is Jackie, and today my final exam is about using Cuda parallel computing to QuickSort, and my professor is Lin Zhenghong. Okay, let's get it. And what is QuickSort? QuickSort is you need to the first one you need to select the pivot, and QuickSort first select an element from the array as the best value called pivot, and there are many selection methods such as selecting the middle element, the first element, and the last element, or the random element. And in my case, I select the middle one. Yeah, so you can see the right side, the array, and they pick up the 6 as a pivot. Yeah, and the second step, you need to use the partitioning. The entire array is rearranged so that all elements smaller than the best value are placed on the one side of the best value, and element greater than the best value and placed on the other side. Once this step is complete, and the place value is in the final position. So you can see the right side image. They will pick up the one pivot, and then they will divide the tube side. One is smaller than the pivot, and the other one is more than the pivot. And the next step, you can see the recursive sorting. QuickSort operations are performed on the subscription to the right and left of the benchmark value, which includes selecting the benchmark value, partitioning operations, and then recursing. This process is repeated until all the subscriptions are ordered. So you can see the right side the image. The final step, the 10 and the 15 is all this correct sort precision. So they will again and again to do the divide these operations. So they can finally make the QuickSort the array that every element can be sorted in the right position. Yeah. And this image is called the Cuda parallel computing. You can see the left side. The left side is one CPU to one GPU, and then the GPU will return the value back to the CPU. But in my case, we use the CPU to convey their data to the GPU, and then the GPU can share their subtext to operate these tags. So you can see the GPU have the 4 tags, the 4 or 5 subtext to process this value or this data. And then these 5 tags can become the 4 tags to process the other value and other data. And then they will return back the value and the data, and that can make all the process more quickly. Yeah. And in my case, we write the first step is implement the 2 Cuda device function for QuickSort. We have the two function. The one function is the swap, and that can exchange the value of the 2 integers using point parameter. And the second one is you use the partition function, performs the partitioning step over QuickSort by selecting the last element of the array as a pivot and rearrange the array so that element less than or equal to the pivot are on the left side, or element greater than the pivot are on the right. And it returns the real partition index indicating the correct position of the pivot in the array. So this function from the basic from implied mean the QuickSort. So you can see the right side we use the 2 function, and these 2 function we use the device keyword. Device keyword is we use to mark functions that are only available on the GPU, and this function cannot be called directly from the CPU. And the next we will use the global keyword. So I say the global keyword function, and this keyword is used to mark the kernel function, which can be called from the host to execute on the GPU. And kernel function must be confuted with the SNES to set out the execution parameter. And so as you can see, the swap is transfer the 2 integers, and the partition is we use to set up the pivot, and we use to transfer and rearrange the array all the element. In my step 2, we can see we write a QuickSort kernel, and this function we mark the global, and this function is implement the parallel QuickSort using Cuda, and the QuickSort kernel function is a GPU kernel function that partitions the array into the 2 parts and recursively sort them. And when the recursion depth is less than 16, it creates non-blocking Cuda scheme to parallelize the sorting of the left of the right part. And we also write the 2 function is QuickSort and the print data. The QuickSort function is called from the host to left the QuickSort kernel and the signals GPU operation to ensure all computations are complete. And the print array function is print all the array content. And this code shows how to use the Cuda string and recursion depth control the obtains parallel computation. And third one is the lab step, and we write a main function, and this main function is mean how to use the Cuda for parallel QuickSort and make sure its execution time. It starts by creating an array of 10,000 random integers. and then they can organize the memory on the GPU and transfer the array from the host to the device. Cuda even are set up to record the execution of the sorting operation. So this QuickSort function is called to perform the sorting on the GPU, and the execution time is calculated and print. So finally, we can see this sort array is transferred back to the host, and GPU memory is filled. The code afterly to use the Cuda and action the parallel computation. And in this main function, we write some Cuda syntax, like the Cuda even character. We use the Cuda even character to be my start time, and the Cuda even create stop to be my end time. And we also use the Cuda even record to record the execution time. And then you can see we also use the Cuda even since results that can record the stop time or the end time. And that's we use the Cuda function sequence to record or create some parameter or record some execution time. So that's my last step. We use this Cuda function to make sure the execution time. And the last one is my performance. In my performance, we use the 10,000 element in this array, and in this array we can see the iterate and the execution time. In the first iterate, we can see my execution time is the 0.033896, and the second iterate execution time is 0.033628. You can see the first one is, you can see the third one is less than second one, and the last one is less than the first one. So if you iterate more time, you will get a more better execution time. So that's my introduce is about we use the Cuda partial computing to QuickSort. Okay, that's my introduce. Thank you.